And we're now in the information security war room, ladies and gentlemen. In this talk, we're going to take a very broad perspective on what is going on in InfoSec. If some of you turn to your neighbors and see the WOOT t-shirt, you will see the essence of InfoSec as we see it captured on it. The point of InfoSec is getting towards computers we can finally trust. This has been a war that we've been fighting ever since the first computer was invented, and we're losing.
Shall we? So, good morning, which, by the way, is the first oxymoron I learned in English. Just being a hacker. So, who are we? This is Professor Sergey Bratus of Dartmouth College. Yeah, he's kind of like, he got me into this mess, speaking in the morning. And my name is Felix, or FX, as most people know me, and I'm like the Sorcerer's Apprentice in many different forms. So from, not even having a high school degree, but teaching in universities and being part of the Langsec movement, down to being a NATO director in order to secure entire countries, because it's so easy to secure single computers. And yeah, what are we going to talk about is the options that used to be and still are on the table, right?
And the window of opportunity, the tactical window, is rapidly shrinking. This is a call to action. We will issue several calls to action in the process of this talk. I should like to remark that we come from very different backgrounds. Felix is fighting on the front lines, taking down major vulnerabilities and eliminating very costly classes of bugs. I'm, of course, is supposed to be in the so-called ivory tower, far behind the front lines. But this perspective brings us together, and hopefully you will appreciate how it hangs together.
So, let me start with a little bit of root cause analysis. Basically, it's 2014. We can't get projection of computer screens right. Bless you, Rick. And go to a Fry's and put an arbitrary number of dollar bills on a table and ask them to get the secure, actually working computer. You can't buy them. We haven't figured out, bless you. We haven't figured out how to build secure or otherwise correctly functioning computers. So what is the problem? Why is that the case? I mean, are we just too dumb to do it? No, not really, because the actual problem is that we're drug addicts. If you would look like, this is like to the left, this is when you started university, to the right is when you got your PhD. So basically, the real problem is once we have a computer and it is not securable and we can't do anything about it. We can't do anything about it. We can't go back to the shop and say make it secure. And why is that? Well, why is that? Is because there's no liability. I mean, realize the drug cartels and the computer industry are the only two industries in the world that have zero product liability. You can pay as much money as you want, and the first thing it will say is a message box saying, I don't even know what I'm built for, so don't expect anything. Interestingly enough, the drug cartels and the computer industry are also the only two industries in the world that call their customers users. And this, ladies and gentlemen, is basically the absolute root cause. The better business model is selling broken software. Put to an extreme, you should actually take your random number generator, NSA backdoored or not, and generate a random number of bytes. And if you find someone who pays for the random number of bytes, you claiming it's a program, you're good. And then you're replacing bytes and you call them patches. So I mean, if you're really good, you're Apple, and then you actually charge for the patches. And that's the whole point. Selling broken software is the better business model than selling correct software, because selling broken software means your addict comes back and hopes with the next version, the functionality he paid for in the first version will actually function. And this means there is zero money in writing correct or secure software. So, when we think about that, we should actually think about, like, how do we get out of this mess? And getting out of this mess is, if you find yourself in a hole, the very first step is stop digging, right? Because what we do is digging. What we do is we have broken computers, but then we have the security industry, we just, talk to our yellow box vendors and say, help us. And they say, we got your back. All you actually need to do is really believe in us, right? So buy more yellow boxes, put them in your network. You will be fine. You will be secure. And because this is a business of trust, right? We promise you, we secure your network. Everything is covered by the security industry, unless, of course, there's shit happening. That was Heartbleed. That's open source. That's not our problem. Leave alone the fact that pretty much all security products in the world had the Heartbleed vulnerability themselves, and they're the slowest to patch. So this is the hole we're digging ourselves into deeper and deeper. So basically, when I hear line speed intrusion protection system, the first thing I think is, line speed. That gives me an idea of the drug consumption practices in their marketing department. They put a line on the table and let's call it IPS. And because what are you doing? You can't figure out how to write a secure protocol parser, because a secure protocol parser would not need a firewall on IPS or something, because it would not crash on invalid input, right? And evil people will not get code execution. Now, because you can't figure out how to do that, you write 500 protocol parsers in C and put them into kernel space and put that right in the line of the attacker in your network. How is that a good idea? Like, I see 500 reasons how that is not a good idea.
So we have a fire, right? We can't possibly contain complexity. And we have this great idea and this great business model. Let's throw some gasoline on that, right? Maybe that will fix it.
Yeah, it's not gasoline. It's pretty much more like a super tanker full of kerosene that we're putting onto it. I mean, we could actually print little stickers that are like on invitation only for NSA Tau group and put it on our firewalls and IPSs. So the thing is, we actually do have solid data on software quality by now, right? This is, I forgot to attribute it because the slides are, they're so brand new, they're still sizzling. This is from Veracode. Veracode does binary analysis on large numbers of software. And if you're looking, the only software that is worse than security software is customer support call center crap. No, seriously, I mean, look at the graph. When you look into the software quality report from Veracode, it turns out that if you program your firewall in Visual Basic on Microsoft Word, it is more secure by far than anything you can buy from Symantec. This is what we're working with, right? So, as it is put here, we're reporting situation normal, all fucked up, sir. Because the real problem is, you can't buy tools and think they're shipped with skill. It's the other way around. You need to understand what you're actually dealing with, and then you go ahead and look for a tool. Because otherwise, this is what happens. This is how we do network security these days, right? So understanding the actual, there's this German saying that understanding the actual problem dramatically increases your chances to actually find a solution. Dramatically. Because if you're not understanding the problem, you get something like this. And yes, I actually learned pseudocode in order to explain legislation for you. So, how do you regulate computer security, right? So, you take some trends report from your government. And then for each sector in this trend report, you look for a customer trend. And for each customer trend, you look for the vendors that fulfill the customer trend, which is relatively easy because they're going to display themselves in your magazine of choice. And once you have those, you look for the products they market with that, and then if the product is there, then if the product is actually not reporting that it's doing this by now, because it needed to report that, we're talking about regulation here, then the vendor is said to be illegal. Then you take an agency, like we have in Germany, we have the agency called BSI, the Federal Office for Information Security. We actually have an agency that cares about the civil computer security, not only the military security. You take that and you have them somehow evaluate the product, however you do that. And then they return a verdict. And if the verdict is below a certain threshold, then you go ahead and you set the vendor to fail. And once you're done, you check whether the vendor is illegal. If that is, then you take the equivalent of the FTC and basically go to vendor and return with prisoners. Or if the vendor is just failed, then you take the local equivalent of the FTC and go to vendor and return money. And that's it. This is how you regulate an entire software market. Will we get better software? No, certainly not.
Well, right after the perpetual motion.
Yes, and Cold Fusion. Not being the Adobe product. So I couldn't find a picture, so Sergey now has to explain that German saying.
Drive out the devil with a Satan.
Yeah.
The Russian saying goes, if you have a problem with dogs, don't call a wolf for help.
Yes. So that's basically what's happening on the international scale and on the cyber war, quote unquote, scale. Because, well, short excursus, do we actually already have a cyber war? Or do we not? No, we actually do not have a cyber war, and we probably never will, simply because in international policy, the legal situation around war is very well defined. It's well defined since people started to have bows, like long bows, because the moment people had long bows, the peasant on the street, like, the farmer that was drafted into the military, could suddenly kill a knight, because the longbow would actually make it through the armament, through the body armor. That was the moment the knights actually all came together and said, no, this is impossible, we need rules for war. That's where the rules for war come from. This is basically the basic root where at some point the Geneva Convention and stuff came from. The thing is, as long as you're not in what is called an armed conflict, an actual honest-to-God war, or not honest to God, but honest to the Security Council, unless you have that, all those nice rules do not apply. You know what international law is really bad at defining? Rules for peace. So we have lots of rules for war, and not the least, the NATO really doesn't really want cyber conflict to escalate into a honest to the Security Council war, Because then someone wouldn't be able to pull Chapter 5. Chapter 5 is that little thing that makes NATO, that says if you attack one of us, then everyone else is shooting at you. And seriously, the United States and UK and not even Germany wants to go to war because Turkey was too stupid to patch the Windows XP. So that is your point why we're not getting cyber war. However, we have a constant cyber conflict. And the reason I'm saying cyber is not because I think this is the correct thing. I think the only person in the world that is allowed to say cyber without looking stupid is William Gibson. But I'm using the terminology that those people use. So the conflict side of it is, from my point of view, really well described by Stephen van Evra's offense-defense theory. He basically has 3 points when a country goes to war or is more likely to go to war. The first being, they go to war when they think conquest is easy. And we see quite a number of nations right now thinking that conquest on the cyber world is easy, right? The second is they go to war when they either think they have large offensive opportunities or large defensive vulnerabilities. Now, if you keep in mind that in reinsurance business, so the insurances that insure insurances, the United States power grid is classified as a developing country. You have an idea what those vulnerabilities could be that we're speaking about here. We haven't figured out how to build secure computers. Now we have a developing country quality power grid. How exactly are we supposed to secure that?
But fear not, we're going to add computers to that, and we'll suddenly make things better.
Yes. And they're yellow, and they're yellow boxes made in the United States. No, the boxes are made in China, but they're supposed to help against yellow China. Forget it. Good. So this imbalance is actually something that is not measured in politics. The imbalance is something that they have perceived, that they feel. So it's not even hard data that says, okay, we have more exploits than the Chinese, let's go to cyber war. No, it's the perception they have. Now, the perception some of those countries have can be seen in what I call the flipping the finger, using the United Nations as a hand. Basically in 2011, if you think of securing the entire internet, the 4 countries that immediately come to mind are China, Russia, Tajikistan, and Uzbekistan, right? Like, no question about it, who else will do that? Now, those countries submitted a resolution proposal, which was later renamed to a Code of Conduct in end of 2011 to the United Nations, which basically says things like to not use ICTs, including networks, to carry out hostile activities or acts of aggression and pose threats to international peace and security, blah. It says ensure the supply chain security of ICT products. Very funny, China. And establish a multilateral, transparent, and democratic international management of the internet. Very funny, China. The interesting thing about that is the fine print. And luckily, someone was, underpaid enough to actually read the entire document. The fine print was, what they also want is curbing dissemination of information which undermines other countries' political, economic, and social stability, as well as their spiritual and cultural environment. Which basically translates to, okay guys, we promise, I'm not saying we don't do it, but we promise to no longer hack you and steal all your business secrets if you delete all the YouTube videos we don't like and hand us the Gmail boxes of those Tibetanians here that we don't like. That was the proposal. And here you have a clear and documented case of someone feeling really superior in the cyber domain. They think they can pull this shit off. Now, speaking of China, everyone is scared about the evil, advanced, persistent threat. Now the thing is, Sergey and I and a couple of other gentlemen in a panel discussion at Troopers once figured out what APT actually means. Advanced means it worked. A exploit is either advanced or an embarrassment. Either it worked or not, right? Persistent means it worked repeatedly because you didn't do shit. And threat means you have no fucking idea why they break into your network. Hence, it's a threat. Otherwise, it would be a clear tactical situation. What I also find really, really amusing, this is the standard picture that is shown when basically when you Bing image search APT and China and military. If you look closely, either they have the cutest UI for Metasploit I've ever seen, or they're actually playing an ego shooter. So, I mean, like, if you ever been to a CTF, to a capture the flag game, you never have so many people being so happily interested in their computer screens, not eating their mice or keyboards when they actually do hacking. Like, this should be obvious, but actually, when you look really closely, you can see it on their screens.
Yeah, but then, of course, each and every one of us puts on a hoodie and a balaclava when we sit down to hacking. So,
don't you not, like, I don't hack without sunglasses and gloves, like, So, but the Chinese are not the only ones, right? There's also the Russian APT, or what they call Klickskrieg, derived from the German term Blitzkrieg, of course. And they're actually really good at it, and they're actually exporting their weapons because look at this. So in the 20th century, the most widely sold weapon on Earth is the automat Kalashnikova. Did I say that correctly?
absolutely.
Thank you. Or also known as AK-47, right? Now, in the 21st century, the most widely used cyber weapon, quote unquote, is a botnet. They're both Russian products. And if you want to see how, like cloud operation, for example, should actually work, rent a piece of botnet. They are where the cloud providers want to be in the future. You can, like, already 10 years ago, you could deploy a piece of code, say run it on 10,000 nodes. Those 10,000 nodes are not even theirs, leave alone they're on and maintained. But you will guaranteed you have a personal contact person. You can call that person every day, every night. You have guaranteed execution on 10,000 nodes plus, and you get your money back if it doesn't work. One reason, because the Russians in RBN, for example, the Russian business network, big bulletproof hoster, they have figured out how product liability works in IT. If a network administrator or system administrator makes a mistake, they drive to his house and shoot him. That is not a joke. This actually happens. So they have really, really highly incentivized administrators.
A point of interest is that we started to look what APT is called in Russian. And you know what it's called in Russian? It's called APT. Advanced Persistent Threat. There is no Russian name for the phenomenon. Because why would you need to pick a fancy name for yourself?
Yes. Yeah. Why is there, like, has there long been no no slander equivalent for white male people that have a job, right? Because, like, what do you need it for? So what happens, right? What happens is that the international policy people come up with ideas. Well, those ideas are, of course, provided by their advisors, also known as lobbyists. And those advisors advise them, we should regulate those cyber arms, which translates to regulate everyone else working in this domain because we want to keep selling this stuff. And this is what actually happened. So in the end of last year, December 2013, the WOSENIX agreement, which is the international agreement that says like what is a regulated weapon, an arms-controlled weapon, and system to produce arms-controlled weapons, got two updates. One update is Intrusion Software. So Intrusion Software says software specially designed or modified to avoid detection by monitoring tools, right? Or to defeat protective countermeasures of computer and network capable devices performing any of the following. Now, one of the 2 points, the extraction of data or information from a computer or network capable device, or the modification of system or user data. And the other, the modification of standard execution path of a program or process in order to allow the execution of externally provided instructions.
Let's think about this for a second. What do we know of the standard computing artifacts and products that fit that definition? Modifying the standard execution path. Well, we call this a debugger. We also call this a dynamic linker loader. We'll come to that. We'll come to that. So the WOSENIX arrangement stipulates that debuggers and reverse engineering tools are exempt from intrusion software. But the way something becomes a product, a thing, an artifact, is that it doesn't start as a pre-named exempted category. It starts as something else. Most of the modern reverse engineering techniques and most of the modern debugging techniques started as hooking and diversion techniques, as unorthodox debugging. And now that is not going to be a debugger on the day it is born. It is going to be a proof of concept. It is going to be an exploit. It is going to be a piece of code that you will find on BugTrack or on Full Disclosure. Before detours became a product, it was a trick. Before we saw unorthodox users, before we saw the non-executable bit, it was a trick. So now the tricks are becoming export controlled. The WOSENIX agreement also stipulates that the controlled items are those that lead to development, generation, or management of intrusion software. So now we've banned compilers and fuzzers. Now we're arms controlling fuzzers and compilers and exploit development toolkits. Because, of course, the only way we progress as an engineering discipline is by moving functionality from programs to tools. Right? We used to write the conditions of our loops in assembly. Now the compiler does this for us.
Yeah, we have to be fair. It is in the WOSENIX agreement, those two things, and there's another one coming up, are in the section of dual use items. So to quote Dan Gear, everything on a computer is dual use. Show me differently. So it's not like you're not automatically violating international law and regulation when dealing with them. However, it is a lot easier, for example, in bilateral agreements to say, well, we exclude category 4 from our trade agreement, for example. Now, the other update of the WOSENIX agreement is one where you can see why stuff actually ends up in regulation. The other update is IP network communication surveillance system or equipment and especially designed components, therefore having all of the following. Point one, performing the following on carrier class IP networks. Analysis, application layer 7, extraction of selected metadata and application content, voice, blah, 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 indexing of extracted data, and secondly, being specifically designed to carry out all of the following: execution of searches on the basis of hard selectors, and mapping the relational network of an individual, group, or people. And you go like, cool, Facebook is outlawed. But in fact, what happens is it is not allowed to produce the algorithms, code, devices, or whatever to do that in carrier class unless, and here's lobbyism in full color, unless you do it for marketing purposes. Anyone remember a former search engine that paid for this particular exception to be put into that? This is Google in all color. The second one is network quality of service. That guy came from Akamai. And the third is the quality of experience for shoppers, and that's an Amazon lobbyist. So here you go. This is how that works. This is called an economic moat. Basically, everyone else can no longer enter this market because it's now regulated, and the ones that are already in the market now basically have peace of mind and can, milk the customers. Now, Sergey.
We are, in this area of ours, in a very strange situation. We're likely to get laws and regulations before we actually have textbooks. Do you know a comprehensive offensive textbook in which a well-meaning legislator or activist could find a definition of an exploit? And the answer is no. We are speaking this very flexible and convenient professional jargon to each other. When legislation will get written based on what journalists hear of this jargon and transduce to media, and from there it goes to actual legislators, what do you think is going to happen but the broken phone effect? So we are in this position when legislation is likely to not even have a textbook or even a dictionary to fall back on. In this recent issue of Login, you will find a call for action to all of the offensive security and defensive security researchers to put aside what we're doing and go to this boring and non-rewarding task of starting a dictionary, just the textbook dictionary of our terms. What is an exploit? What is, God forbid, a weaponized exploit? How do we do QA on exploits? What does it mean for software to have withstood a particular exploitation?
In contrast to software, QA on exploits is really easy. Gives root shell, does not give root shell. You can't argue with a root shell, and you can't argue with the absence of root shell.
Well, an exploit is like a natural law. It runs here and now, or it's bullshit.
Yes. So what I would also like to point out, because I forgot to do that, and it's relevant here, these section slides. This is a graphic done by a hacker by the so-called Internet Census 2012, where he took over 140,000 default password routers around the world and used them to nicely scan the entire internet for a while. And then gave them back, actually. He fixed the devices and gave them back to their respective owners. And we see here the usage of IP addresses geomapped on the planet. Now, this is the same group of people that are killing themselves right now with stupid legislation. Meaning, in the best case, we're just like biting our ass for our own legislation later on when Africa actually starts using computer at a larger scale, because they're not going to have those legislations, and they're going to look at us and go like, and so you outlawed your best people? Stupid. But hey, now it's our market. Good. Talking about the best people. So, given this this legislative trend, what about the hacker research? What about the free publication of exploits, of vulnerabilities, full disclosure and all of that? Now think of full disclosure. Think of where full disclosure actually came from. Full disclosure was also a child of the lack of product liability. The reason was, back in the days, in the 80s, you had, let's say, Solaris, God forbid, and there was vulnerabilities back and forth, and you try to secure your Solaris box, and then Sun will tell you, nah, we're not going to fix that. We send the programmers to write more Java. And the only way to actually get the fix for a known vulnerability was public shaming, also known as full disclosure. Now, think of this. Writing patches costs money. And it doesn't make you money, as I said, unless you're Apple. Having to apply patches in companies, and this is pervert, but it is the case, also costs money, right? So the hordes of people that have to patch systems, that have to verify that the patch doesn't bring down your trading platform, and all of that, they cost money, they cost you time. They're not making you money. So it is to no surprise that certain company lobbyists, advisors to the government, from Oracle and Apple and similar, advised that outlawing full disclosure, making it arms trade, actually has a benefit to a large economy like the US, because once we get rid of the hackers and of the full disclosure, the vulnerabilities are simply reduced to a PR problem, which means we can actually get rid of the patches as well. And we can get rid of the guy who applies the patches. So we actually make money for the entire economy by, making sure that those few unwashed punks with the hoodies keep their fucking mouth shut. Which then, of course, makes hackers arms dealers, as this retired expert from a well-known legislation group tells us here. But so what about the root cause? Are there even people that try to do something about the root cause? Yes, and I am one of those, because I realized, wait, so we can't reintroduce product liability for software, right? If it would do that, it would go, bang, here is Oracle, bang, here's SAP, bang, here's Microsoft. That would disappear in a day, right? So we can't do that. However, how about special users? See, I'm using the term user here. When you consider that the Department of Defense in average spends 80 months from the order of a new software to the potential put in use of the new software. That's about like an era in computer time, like 80 months. That's nice. They spend about a year just testing. Now, they have basically the same drug addiction problem that everyone else has, just in bigger scale. And let me tell you, when you talk to, let's say, space people, they know that problem because their maintenance scenario is a bitch, especially since there's no longer space shuttle flights. Because you have to get someone up there and fix the whole thing. So I thought about that and then realized, well, the military also always had special requirements for stuff. So why is their camping equipment better than everyone else's? Because they camp like it is their job, because surprise, it is their job. So they have better camping equipment. Why wouldn't they be able to ask for better security? Because they need better computers and working computers. And the moment you have liability for certain military acquisition sites, and funnily enough, the military people I talk to really like this idea, because the moment you have liability there, a company like Oracle can't sell software to the military. They will continue to do so, but the first time they get the counter check for, we paid you 50 million, now you pay us 500 million in damages for, this damage that your so-called database did to our mission data. Nom 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 nom. So, in that moment, they can't offer anymore. So suddenly, there is a lot of money in writing secure and functioning stuff, because you're the only one who can sell to the military, and the military tends to be a good customer. Which then triggers basically venture capitalists going, what's this small company that builds the microkernel and nothing else? And wrote this code and then reads this code and reads the code and reads the code and reads the code. How do we get secure software? Look at Apache 1.3. You write a server, you patch it, you read it, and you never touch the fucking thing again. Ever. Features? No features. Now, I am actively working on this hack in the hopes that it becomes NATO purchase regulation. The thing is, well, the next thing that happens is they will ask us, yeah, okay, so now we want to write secure software. How the fuck do we do that? And how the fuck do we measure whether it is secure or not? So, in the meantime, until this happens, we also need, and Sergey is going to answer the how the fuck questions. In the meantime, until we actually have areas of liability, we can also go ahead and make security actually as something that makes people money and not as a cost center. And one way is by applying Langsec to making security make money. Basically, people are scared of grammars. This is why everyone writes shotgun parsers in Python, and then, Python is this programming environment that transfers user expectation to stack traces. It's a sibling of Java that transfers user input to XML stack traces. So basically, because everyone is scared of grammars, except for legal people, because what they do when they talk to each other is hammering out a grammar for a specific case. Nobody uses grammars, and hence everyone uses ad hoc blah blah stuff. But what if we can provide something, basically an interface that makes this agreeing on stuff between different departments in, let's say, in an enterprise, makes it easier. And so I came up with this very, very simple machine, so to say. Basically what you do is everyone sits on one table and says, like, what data do we need to transfer? Now, the prerequisite here being you have strong data types. You have agreed on strong data types. Everyone will do that because nobody knows what a strong data type is. They think it's some kind of fancy tea. And they will agree on that. But now let's say we have strong data types. That everyone sits on a table, lists the information that needs to be handled. In this case, we have a name and we have a sparkle size. And then you have a machine where you enter that. This machine, for example, is Excel, the most widely used programming language in the world. And it will say, well, I stay red because a string is, I can't tell how long a string is, and sparkle size, you have used the signed integer. Then people realize sparkle, which is German for asparagus, sparkle is rarely a negative length, right? If it's a negative length, it's called a hole. Very similar to, how do you call a boomerang that doesn't come back? Stick. So they fixed the sparkle size. The sparkle size is now unsigned. So it turns yellow. And then they changed the string to UTF-8 because they realized Mr. Hyponin is, a colleague of us and he's Finnish. And then the moment you have Finnish or German colleagues, you get little dots on the characters, and you realize what Unicode was for. And then they realize, well, the Spargel is also not infinite large, so maybe we're fine with 32-bit. And then they realize, well, even names have a limit. And then they put like the name's length in there. And then everyone signs off. The funny part now is that the managers sign off because they can read this. And suddenly, what did you get? You got a regular grammar. Now everyone can actually generate the fucking code that talks to each other instead of everyone writing their own code and then having the manager from the other department come in and say, but my Spargel is longer than what you programmed. And this is how you actually use language security to make people money, because they suddenly don't have development time of half a year, but code generation time of half a day. And they can test it. This principle also can be applied to standard committees, because standard committees, designed by committee, the worst possible way of getting a protocol done. They have the same problem, but they have the problem n square. Like everyone needs to talk to everyone else and themselves. And if they're not schizophrenic, that's n square. If they're schizophrenic, then there's added cases. And look at, for example, what do we get standardized? We get standardized everything they called halfway agree on, the rest is vendor extensions. IPv6 being a prime example for that. And with that, we have a segue into the solution, and I leave you with the crazy Russian professor.
Well, it's a tall order to solve security, and obviously we're not going to do that. But what we're going to have a look at right now is where insecurity comes from, right? The science of insecurity is a very high necessity at this point, because when things are broken and all of our attempts to fix them start resembling inventing perpetual motion, then perhaps there is some science that says you shouldn't be doing this. You should be looking elsewhere. You should not be trying to solve a problem that is unsolvable. In fact, physics is largely defined, and therefore engineering is largely defined, by the problems that we know we cannot and should not be solving. There is energy conservation. Computer engineering is also a branch of engineering, and just as in physical world, restrictions imposed by nature apply. However, this magic vision of sprinkling computers on things to make them better completely ignores the fact that there are physical impossibilities in computer engineering, in symbolic manipulation as well. And so we know which problems we cannot solve. We have the concept of undecidability. And we are going to apply that to the science of insecurity. The Langsec language theoretic security approach was co-founded by Len Sessamon, who unfortunately passed away, and his wife Meredith Patterson. And their motivation for Langsec has been secure communication. Len has been cypherpunk, and people in the audience knew him.
We would like to point out that the title is not an anti-Microsoft joke.
So the realization that he came to, and that brought this work to the world, and this is his legacy, is that cryptography doesn't actually solve secure communication. Because before you decrypt, you must parse. And in a world where all parsers are broken, this is when you're already compromised, and your crypto will not help you. So in a world where at communication boundaries, we have hostile inputs handled by code that is exploitable, we have a problem way before crypto, our best weapon, can be brought to bear. And as you may have gathered from our WOOT keynote, if you were there, or from previous publications, crypto is not broken. Crypto must be weakened by those who are interested in doing so. It is being weakened in interesting ways, but still it is a working tool.
One of the few. However, the best example is over 80% of the code in SSH daemons has to be executed before it authenticated you. So how can crypto help you there? Not.
So then we're facing the problem of code at communication boundaries being untrustworthy. And the question is how to make this trustworthy to the same extent that crypto is trustworthy. To the end that there are mathematical impossibilities for that code to run away. We trust cryptography because we trust that certain problems are very hard to solve. We must be able to trust our input handling code at our communication boundaries on the same fashion. So what we need to do is model computations induced by inputs. This is a hard problem because, you know, what do you call code meeting a crafted input? You call this exploitation. So, and this is, by the way, modifying the execution path, right? Any input modifies the execution path. Any input is, in fact, a program.
And if you remember what we just saw about the WOSENIX agreement, it makes your input illegal.
How on earth are we supposed to communicate and study the artifacts and automate the production and generation of those artifacts if we must have protection of lawyers at all times? I mean, we're not a carrier group, right? Accompanied by guided missile lawyers or something like that. So we must model computation induced by inputs. And we must reduce that computation in complexity to the lowest possible, most formally definable state. And so there is actually a theory that connects inputs, consuming symbols, consuming bytes, with computation. And it does so via this process called recognition in formal language theory. In formal language theory, classes of inputs are defined corresponding to the computational device needed to recognize the language. So this is the famous Chomsky or Chomsky-Schutzenberger hierarchy, which starts with regular languages, those that you can recognize with finite state machines. Then context-free languages, where you already need push-down automata. And then context-sensitive languages with various subclasses, such as weakly context-sensitive. This is where you start seeing length fields. And some length fields are not as bad as others. A length field next to the field whose length is described is not as bad. Length fields that must agree across swathes of input are much worse. And the more context sensitive you get, the higher the computational complexity of the recognizer automaton. So you go from finite state machines, which we know how to verify, to push-down automata, where the first undecidability traps await, then to linear bounded automata, and finally to Turing machines, where the halting problem awaits and devours any attempt at checking even liveness of a program. Will it loop forever?
And I would like to ask anyone who has, a commercial or open source web application firewall protection thingy that prevents SQL injection by using regular expressions of known attacks, to look at this diagram and reconsider where the regular expression could be applied and which class SQL or HTML belongs to, and how useful your protection device actually is?
Well, the answer, of course, is that it is likely making your system more vulnerable. In fact, anti-XSS protections in, say, IE8 actually made pages that were not vulnerable to XSS vulnerable to such by rewriting, using regular expressions to rewrite context-free language expressions known as web pages, and actually introducing the vulnerability, which could then be exploited. Any code that you introduce is a part of the machine that the attacker, the exploiter, is going to borrow from you to run their code.
We would like to also point out that the genius engineers at Google managed to do the same thing, but on the server side.
So, but the gist of this hierarchy is extremely important. It is this extremely important observation that we already know how to characterize computation whose point is consuming input and staying within the well-defined model of states, state transitions, and so on. And this should be used on every communication boundary, and it isn't. So exploits have been exercising this connection, and the leading exploit development schools of thought have been aware of this connection for quite a while, right? The most flagrant example is relatively recent. It's web apps. And if you define web apps as where recursively nested object inputs are validated with regular expressions, you wouldn't be too far off. This is why nothing on the web can be trusted. But the mismatch between the expected input and the assumptions that subsequent code makes and the recognizer that is supposed to enforce those assumptions is the recipe for any famous parser bug. And we are talking SSH pre-auth, we are talking IPv6, IPsec pre-auth, and so many, pretty much everything. We are going to see some recent examples at the end of this talk. So we propose to patch the Postel Principle. Instead of being liberal with what you accept and conservative with what you send, you have to be definite about what you accept for the sake of your users. These are the rules of engagement. Input can only be trusted after they have been fully recognized in the formal language sense. We must fall back on the formal model of computation that consumes input and constructs data structures. Inputs that have no definition that can be so recognized should be deemed untrustworthy. They cannot be trusted. If you do not know in what states your code can be, into what state your code can be driven, you are already pwned. Moreover, communication boundary code that does not implement a recognizer based on the appropriate formal language definition and the appropriate grade in the Chomsky hierarchy cannot be trusted either. If it's not recognized, it shouldn't be processed.
And we have to we have to wake up and realize that that Postel's principle was the right thing to get a let's say military-sponsored research project that happened to be too useful to universities off the ground. But now, you know, in a society where pretty much everything hangs off that former research project, and it's good enough that the military that had it built now actually wants it back, we actually should also play by different rules, like by the rules of adults and no longer by the rules of kids that write protocol parsers.
So, in a slogan, the essence of a language theoretic security, this approach to fixing the communication boundaries, is that any input is a program, any input whatsoever. Input becomes code the moment it starts driving it from state to state along some transitions. If you are hitting some state that you did not anticipate, then you find yourself being programmed remotely by the attacker. Any input is code. And when I told this to Greg Morissette, he said, of course, we've been saying it all along in the languages theory. Everything is an interpreter. Except, of course, for our interpreters and compilers, we generate code that parses those languages from a formal grammar, unless, of course, this is JavaScript, deployed in every browser, including yours. But we're not doing this anywhere else, and we should. The essence of exploitation is unexpected code and unexpected state. So exploitation is magic, right? Let's think everyone's favorite pony cartoon here. Exploitation is magic. Instead, I will steal a quote from Arthur Clarke. Any sufficiently advanced technology is indistinguishable from magic. No. Any sufficiently complex input data is indistinguishable from bytecode. The code that must interpret it is indistinguishable from a virtual machine to that bytecode. Parsing complex data is being remotely programmed. Everything is an interpreter. Therefore, every system is programmed by input. Think of the string being matched by a regular expression as a program, and the regular exception itself, and the regular expression itself as a machine. The string is the program. This is how it is. This is what drives the state transitions in the regex, of which we all learn in school and then promptly fail to apply it to any other kind of input processing. Same for the inputs to a finite state or push-down automaton. The input is the program. Same for the tape of the Turing machine, which is our best abstraction of computation. Same of any code whatsoever when it reads data. And exploiters have been using this since at least LF1's exploiting, overwriting the stack for fun and profit. Standard function prologues and epilogues are in fact an automaton. Those push EBP, move ESP, EBP instructions are a distributed automaton that realizes the abstraction of the control flow graph. Its program is on the stack. And from 1997, when Solar Designer first figured out the return to library, and others figured out return to PLT, to the dynamic linker, to Tim Newsham, who figured out how to chain fake stake frames together, to Hera, who in 2000 posted on BugTrack that, hey, you could actually implement any program in this fashion as a series of fake stake frames. To Nurgle, who described this in Frac in 2001. We know this thanks to Hovav Shacham as the return-oriented programming. And this has changed our threat model from malicious code, that everyone and their antivirus brother were looking into, in the network traffic, to malicious computation. But it has not changed our threat model enough. Heap management code is a machine. The contents of the heap are the program. Once Upon a Free and Voodoo Electrics in Frac 57 demonstrated this quite conclusively. An instruction set architecture was found in Doug Lee's malloc and other implementations of malloc that gives you a basic move of a value to another address. Write 4 bytes almost anywhere if a double free occurs somewhere in the program. The configuration of this machine can be performed with malloc calls. For example, Alex Soterov's heap feng shui, massaging the heap to get chunks distributed on it in a certain way and objects allocated in a certain way. This is instantiation of the weird machine that runs this instruction set architecture. So Examples of general programming being done in such weird assembly abound. The stack, of course, is a program. The heap is a program. Internals of objects are a program if you think of constructors and destructors. Okay, of course, format strings are programs, and those have been
by design for a change.
Yeah, and you know, whoever read the manual, whoever reads the full manual of your processor, right?
I do.
Well, this is why we're standing here preaching. Think of the basic mechanism of a double free, right? A forward link and a backward link in a chunk in the doubly linked list that connects the chunks is being overwritten to exclude a chunk from the doubly linked list, right? In that you take a flink and the blink, and you take this 4 or 8-byte integer, and you write it at the location specified by its neighboring 4-byte or 8-byte integer. This is a move, and it goes in the frac paper by AA, almost anywhere 4 bytes, right? AA, B, M, O. The recent addition to this collection is SIG return-oriented programming from this year's Oakland, and it goes on and on and on. The machines inside the machine are many and varied. We have been alerted to all of those execution models, to all of those programming modes, to all of those ways that execution paths can be manipulated by input in a constructive and Turing-complete, as it turns out, in fact, in most cases, manner, by the co-evolution of defense and offense. So WOOT this year started its CFP with John Lambert's quote, if you shame a tech research, you misjudge its contribution. Offense and defense aren't peers. Defense is offense's child. The meaning we put into this is that offense provides the computational models for defense. Without the computational model, you cannot defend computation.
If you doubt this statement, go out, find someone in those like green funny dresses that go to the big ships, and ask them about defense and whether they invent defense without being, you know, forced by an offense force to ever have that.
Remember the Wassenaar arrangement and its dual use of computational diversion? This threatens to stop this coevolution. No matter how you interpret this, this is something that is likely to put major brakes on this co-development of offense and defense. This means more vulnerable software, not less. So Turing completeness, which I mentioned, ROP is Turing complete. We have shown that metadata of ELF and MECO and actually PE as well is Turing complete. It's largely a distraction. You do not write your entire program in the weird programming modes. Those weird machines inside your code, those architectures on which exploits run, or you might say emergent architectures for unexpected computation, they have this nice theoretical property, but in practice you care about a root shell. However, bring your own linker, reliable composition is a thing. This is how, after this coevolution in the presence of defensive measures, you must achieve that composition of your exploit and the target so that you don't crash the target. Bring your own linker. This has actually been, this aspect of composition has actually been the focus of the hacker community as well. Sylvia Cesar in 1998 showed how to load kernel modules into a kernel that doesn't support kernel module loading. The GROG and the RSC team did the same for ELF, and ELF shell opened up for creative ELF rewriting, and so it goes on. Yet these were the only sources up until not so long ago where this dynamic linking information, dynamic linking mechanism was documented. Where does this put us in academic context? What we do to inputs is validate it. And by the way, if you hear about sanitizing data to remove bad characters, or run away. This is an anti-pattern.
No, write an exploit.
Oh yes. Yeah. So maybe you should be evolution to that target.
Yeah, it's like active Darwinism, right? Like if someone comes up with sanitizing data, you write an exploit, they lose their job, so you keep the gene pool of programmers more clean.
Or something. So what we do with code in the land of formal methods is we verify it. We establish properties such as we can establish with formal methods. Now that data is in fact code, now that inputs are in fact programs, once we realize that, then we know that we can only trust data, we can only trust an input if we have verified what it can do as a program. Validation is verification. There is no middle ground. Compare this with the new trend in academic research, automated exploit generation. This is a quote from a paper by David Brumley's group, recently published in CACM, summarizing their previous research. And they frame automatic exploit generation as a program verification task. The task becomes pretty much finding the exploitability path in the same way that you find that you verify properties of an executable system, in the same way as you formally prove properties of a system. This is the only way to approach this issue on the firm theoretical foundation, and they're doing it. And by the way, is this arms dealing? Well, Wassenaar might tell. Verification is hard. We continually run into the halting problem, into undecidability. We cannot verify non-trivial code properties. Rice's theorem, your standard example is that you can't even verify if the program you input squares a number. You cannot, of course, verify if, in a general way, if a program holds, which we know as liveness, and the absence of this as a DOS attack. So Turing-complete systems are very hard. Luckily, nothing at the communication boundary needs to be Turing-complete. So security, in any real sense, cannot be attained if we need to solve the halting problem to achieve it. So statically deciding what the program does is a really bad bet if your program is in a rich language in the Chomsky hierarchy.
If you know anyone like working in the antivirus industry, do me a favor and tell them about the halting problem. Just, Symantec seems to think that, just because they make $3 billion a year with AV products, they have proved Turing wrong.
So it actually gets worse. Statically deciding if two parsers interpret the message the same is hard. So we have this undecidability cliff. Once you leave the comfortable space of regular and context-free languages, once you start with context sensitivity, which means, by the way, variable length fields that must agree across code, and so on, you fall off of the undecidability cliff. Your aliveness of your web page, which is HTML5 and CSS, or whatever effects it has on your memory, is an undecidable problem, because HTML5 and CSS are Turing complete. And by the way, ELF metadata has the same problem. Equivalence of parsers such as of your X509 certificate parsers, is again undecidable because it becomes undecidable starting with non-deterministic pushdown, that is to say, way past ASN1, and this is why X509 certs are broken. So we should shift the focus of verification from the problems that we cannot solve to those that we can. And I'm quoting here Karl Marx. Of course, I grew up where I had to study his legacy. And philosophers have only interpreted the world. We must change it. And what followed, of course, had a lot of hammers and sickles and not so much grain and bread. But verification efforts tend to regard computing tasks as preset and given, whereas we should be having a simpler set of recognition tasks, a simpler set of verification tasks to solve. Simplifying languages of data formats pays off. You should not paint yourself into the corner of solving the halting problem. So recognizers are everywhere. Recognizer bugs are everywhere. If you look at the parser bugs that dominate the ponies, and those are the bugs that got the most publicity, let's just look at the last few years. This is Heartbleed. Heartbleed is a parser bug.
We're skipping over that because we're getting out of time. This one everyone knows. This is how you mistake things. We shall conclude here with the fact that we had the first Langsec workshop ever, right, at IEEE S&P. So we're trying to talk among people and help people to stop playing with themselves and actually doing something useful for the world, because this is now academia's turn. Academia is the right place to fix all that, and this is what Langsec aims for, and also why we even have marketing trainings there.
So all the papers are now online. The workshop took place in San Jose in May 2014. It covers parsers and communication boundaries of all kinds, from PHY to app layer. With that, it's your turn.
Thank you very much.
I want to just thank the speakers because that was thrown together between midnight and 3 this morning. I should tell you though, I forgot to warn Felix that this wasn't a HackerCon, and I apologize for anyone who might be offended by the language. It's in another it's from another world. Please accept my apology. That was my fault. Thank you for an absolutely amazing talk. Much appreciated. Let's thank the speakers.